Jordan Gerth, a scientist with the National Weather Service Office of Observations in Silver Spring, Maryland. I've been in with the National Weather Service and NOAA for almost 4 years now. The National Weather Service is part of the National Oceanic and Atmospheric Administration, which has broad responsibility for environmental sensing, stewardship, and science. The National Weather Service's mission in particular is to save lives and protect property through weather forecast and warning. We want to help communities understand the impacts of weather, particularly when the weather becomes severe. We fly weather satellites in largely two orbits. One of them is a low Earth orbit. The other one is a geostationary orbit. The low Earth orbit has satellites that go around the Earth approximately every 100 minutes or so. Those have a radiometer. And so our radiometer, as it flies overhead very quickly because it's making a full orbit of the Earth every 100 minutes, is essentially a power meter that's capturing over a relatively small area the power, or if you will, the emission from the molecules that are reaching the satellite. And that is then converted to a brightness temperature, which is an indication of the composition of the atmosphere and to some extent the temperature of the atmosphere that's being sensed. In order to forecast weather accurately, we need to get a global picture. And that's really where the satellites come in. So once we identify certain frequencies that are important, we make sure that we have an allocation for them and that our sensors can detect those frequencies. Once we have an allocation for Earth exploration satellite services, we have to make sure that we are not getting any other data from adjacent bands. And that's where the policy aspect of this comes in. There's often a lot of discussion that has to go into how much do you exactly need to sense the weather, and what is the priority, sometimes higher up, even as high as the president, in terms of making spectrum available for other non-weather uses, to support American innovation, to support people's need for information through their cell phones. I mean, anybody that has designed a telecommunications system, as you mentioned, it's receiver, transmitter. In our case, we just have the receiver. In a transmitter-receiver relationship, you have a signal. Our radiometers, our power meters are looking at the background. That's all the information that we're getting. We have really no way on a simple radiometer to discern the source at all. If it's in that frequency, we're going to pick it up. If we're looking at water vapor, we're around 24 gigahertz. We can't move. The water vapor molecules, the oxygen molecules, they're always going to emit at those certain frequencies based on their characteristics. There's not a special signal that tells us, oh, I'm an oxygen molecule, like there are with telecommunication systems. So it's not just the visible, but additional near infrared and infrared bands. We bring that down 31 megabits per second is the amount of data that we have to bring down. And then there's some ground processing that goes on, and then some of that data is then relayed back through the satellite, Earth to space, and then space to our partners. So if you're an academic institution, you can receive this data from what we call our GOES rebroadcast. GOES stands for Geostationary Operational Environmental Satellite rebroadcast, and you pull that data in and then use it for scientific studies, or if you're at a weather service office, use it to issue those forecasts and warnings that are so critical. The frequencies that are very critical in the passive microwave are typically between about 20 and 90 gigahertz. 24 gigahertz is a water vapor band. If there's any band that is so vital for global weather forecasts for that 7 to 10 day prediction, it's 50 to 60 gigahertz, because it helps us construct an entire atmosphere, understanding temperature. And then there's up around 90 gigahertz, some additional frequencies that are important for, again, seeing inside the cloud, understanding cloud ice, cloud water, and how storms are developing. You can have this general band that is sensitive to, in this case, oxygen. But as you make those bands more narrow, what you can end up seeing is deeper into the atmosphere, because the oxygen that's higher in the atmosphere is providing less of the signal up to the radiometer. So it's very critical not only that we have broadband sensors, but that we also are able to use the characteristics of the molecules to profile the atmosphere and construct a representation from the surface or near the surface on up. We just decide, again, what capabilities we need, and then we have various announcements to have our partners propose at multiple stages. What kind of technologies should we be aware of is the first step. And then as we advance in the project, we define more requirements, and eventually we'll have contracts out there for instruments, and those contracts are sometimes in the hundreds of millions of dollars, and we'll then purchase those instruments from our industry partners and fly them to meet our needs. And we need bright minds. If you like a challenge, if you're a student looking for a challenge, don't overlook NOAA. I mean, a lot of folks think about NASA, perhaps a slightly more visible agency, but we do satellite operations here. We're part of teams that build satellites. You can, of course, work for any number one of the industry vendors on multi-year projects to supply instrumentation to NOAA if you want to innovate on that end. There are so many different things you can do without even having a meteorology background. We have an exciting mission, and it's never ending. It's nonstop. We have missions that have to fly because we have a responsibility to sense the atmosphere day in and day out.